Howdy folks, welcome back to CS 128 Honors. In this lecture, we're going to be continuing on from the last lecture on smart pointers and generics and talking about how we can finish implementing that singly linked list that we showed the implementation for in the slides. So today we're just going to continue implementing that linked list and give you some starters for homework 8, so hopefully that makes things easier. Okay, so fair warning. For the sake of this course, implementing your own linked lists in Rust is a very bad idea. There are a lot of consequences that ownership has on how linked lists work and owning things, so you need a lot of smart pointers to make your life easier, but that just complicates things. You can use unsafe Rust, but we're not going to teach you unsafe Rust to implement linked lists. So if you ever want to use a linked list in your code, just please use a standard libraries implementation. It's a lot easier. This is just a sort of exercise to teach you generics and just show you why this is a bad idea. Okay. Like I said, ownership rules complicate things. So stick to the standard library if and when you can. Okay, so we said this is a bad implementation of linked lists because we don't know the size of our type link. One link could potentially have another link inside. This link could potentially have another one and another one and another one. So Rust cannot tell how big this link is when the code compiles. We get this recursive type has infinite size warning. The first link contains a potential other link and another link and another one. And so we fix this with a box. So we change our functions or our type signature to instead of containing an option to a link t, it contains an option of a box. So our box says that this link is going to be stored somewhere on the heap. So at compile time, we don't need to worry too much about how big that link is. Okay? So this is the implementation you're going to get for homework 8. So we're going to work on implementing some functions from homework 8 to give you a head start. Okay. So in homework 8, you are given this type definition, you're also given this type definition, and you're going to be implementing some functions for it. So you have your constructor here, you get a new instance of linked list that is empty. So I'd imagine your length starts out as 0 and your front starts out as a none, or there's no links yet. And then length, we're giving you this length variable to make your life easier, hopefully. And then the is empty, again, use a length variable. And then, so we're going to ask you to implement two functions, add front and add back. Add back is considerably more difficult. So we're going to be walking through how to complete that. And hopefully that inspires you on how to complete add front on your own. And then to help you test your code and debug, we give you this helper function 2vec, which takes your linked list and it converts it to a vector and returns that. So hopefully you can try things out and use this function to debug your own code. And finally, we ask you to implement this link constructor. Hopefully this is also easy. Okay. So with add back, we need to do a couple of things. So first, we want to iterate through the linked list and find the final element. So and then, so once we get to the final element, if our list is empty, there's no last link. So, there's nothing we can add to. We want to change this front pointer. So our list is empty, we want to change the front pointer. If it is not empty, we add a link to the the last link. So if list is empty, create the first link, else add a link to the last link. Okay. And then finally, we gave you that length metadata. So just update the length. Okay. So the first part is the toughest one. 2 and 3 should be fairly straightforward. It's just, a couple if statements. But this is where things get tricky because we're sort of iterating through links and taking the next one and trying to find that last element. So we're going to be using a while loop because we don't know the size per se. And so we can just sort of traverse through our linked list and get that last element. So we're going to need a variable to keep track of where exactly we're at in our linked list. So we're going to make this mutable because we want to change where our current pointer is. And it's going to be a mutable reference to this next, because we want to be able to change the next pointer of a particular link. So option of a boxed link. Okay. And so we're going to start out at the front of our list. And so we have a mutable variable, which is a mutable reference to an optional box link. So we start out at the front and we're going to iterate through. So while our current variable is not none, so if it is some, if our current link is some link, we can traverse potentially to the next link. And we want to check if the next link is also valid if the current is not the last one. So if current is not the last one, we can move on in our iteration. So there is this special function on the option type that basically takes in a reference to an option, and it converts it to an owned option of a reference. So slightly tricky, but you convert from this ampersand option that you get from our iteration, which is a reference, and gives you an option of a reference. Okay. Then with that, we know that this is some, so we're able to unwrap it. And so now we have a reference to this boxed link inside. Okay. And so we're going to take the next and check if that is also some, if we can continue on to the next link. Okay. So this is where we do the iteration. This is where we move this curve pointer, this curve mutable reference, to the next link in the list. So current is a mutable reference to, okay, so this is the tricky part. So we want to get a mutable reference to this next boxed link. So same principle with asref, we're going to use this function asMute. So asMute is the same thing, except it takes a mutable reference to an option and converts it to an option of a mutable reference to your contained type. So you basically get a new option that's a wrapper around a reference. So this is the tricky ownership bit. Okay. So we know from here that current is some. So current is not a null pointer. We're not at the end of our list. So we're allowed to unwrap this for the same reason we are here. And then we can just move on to the next one. So we convert our mutable reference to an option of a mutable reference, unwrap that, and then change cur to be that contained boxed link. Okay, so we've iterated through the list, and assuming this while loop condition fails, we're at the last link in our list. So current is either none in the case that our list is empty, or the next link is none. Either of these two conditions failed. So we're going to be using this length metadata variable to sort of keep track of if our list is empty, and then do some checks based on that. So we said if our list is empty, we want to create the first link, which means we modify this front variable. Otherwise, we add on to cur. Okay, so if the length is 0, we're going to change front to a sum of a boxed link. So sum of box new, and then link new. So you'll implement this link constructor yourself, and we get in this thing data to pass into that constructor. Okay, so an option of a box of a link. Otherwise, if we're not at the start of our list, we're going to tack on a new link to the end of cur. So cur's next. So again, same principle. We want to get convert a mutable reference to an option into an option of a mutable reference. So then we can access and change that mutable reference. So cur.asMute.unwrap. We're able to unwrap it because we know cur is sum right now. Get the next pointer and also change that to an option of a boxed link. Okay. Now that we have that, we just update the length variable, and we're good. So, pretty straightforward. This is the only difficult part. It's figuring out that we want to access the box inside. So we need this asRef and asMute function to get proper references to the inner data of the option. Okay. So it is on you to implement add front. You can sort of scope out what you need to do for that. So again, 3 things. First is create the new link. So you'll use the same syntax that you did here. Sum, box new, link new, thing. 2, you're going to want to update the head pointer. So you're going to check if it is none. If it's none, you can simply just change the head pointer to be whatever new link you have. If the head pointer is something, then you're going to want to make this new link's next pointer be the current front pointer. I'm using head and front interchangeably. They're the same thing. The front is the head of the list. So this is the tricky part. I would look into option.take. This will take ownership of an option out of this variable. So take ownership of this. So I recommend your implementation uses something about option.take. And finally, like we did, update the list metadata. So increment the length by 1. And then hopefully these 2 functions should be trivial. This one should also be pretty easy. Same thing with this new link constructor. Okay, so I'll pause the video right here if you want to take a reference, take a screenshot, or just copy it. And hopefully this should give you a good start on the homework. Okay, and scrolling back up to main. So we're creating a new linked list. We are sort of converting that to a vector and printing that out. And assuming we've implemented things correctly, this sequence of instructions should print out 1, 2, 3, 4, 5. Because we add 2, 3, 4 to the back, then add 1 to the front, and 5 to the back. Okay, so you can use this code to test out your own implementation. But that is all for today's lecture. Thanks for listening. Take care.